Okay, so we have been looking at reasoning in propositional logic, and today we want to look at a more recent method known as the resolution method. This was given by Alan Robinson in 1965. So, it is a fairly recent method if you compare it with, for example, Frege's axiomatic system, which is more than 200 years old. This is quite recent, and it was motivated by the fact that you want to write computer programs to generate proofs, which means you have to find proofs automatically. Now, if you look at the high level algorithm for finding proof, it basically says pick some rule of inference, pick some applicable data and produce some new data and add it to the system. So, it is basically a search algorithm, which is searching in this space of sentences which can be produced and trying to produce the sentence that you are interested in essentially. So, to motivate this resolution method, let us go back to the problem that we started with, the example that we were looking at, which said that P and R or something like that, R implies Q, P and S implies T. So, I am not using the same symbols, but anyway it is the same problem. And from this we have to show T essentially. Now, if you go back over the proof that we did for this, then this was to be shown. So, this is 1, 2, 3, 4. Then we derived, for example, P from this thing, and there was a rule called simplification. So, we use one rule of inference called simplification. Then we derived R by the same rule. Then from R and R and Q we derived Q. So, 6, 2 modus ponens. So, the second rule of inference we use there. Then from R and not R or S we derived S. So, this is from 6 and 4, and there is a rule called disjunctive syllogism. So, I will just use DS there. Then from this we get, from 5 and 8 we get P and S. And then finally, we get T from 9, 3 and modus ponens. So, this proof required us to use 3 rules of inference: simplification, modus ponens, 4 rules of inference, disjunctive syllogism and addition, and then of course, we have to choose which rule to pick and what to apply it to, and so on and so forth. It looks nice and simple when you look at just these 4 sentences and the conclusion that you want to draw, but in practice the set of facts that are available to a reasoning system would be hundreds of, maybe thousands of facts, and you may want to ask whether a certain formula is true or not. So, it is not that only the relevant things are given to you, there may be many irrelevant other formulas, and there may be hundreds of rules which may be applicable. So, if you look at the forward state space search, for example, like we were looking at in planning, it generates a huge branching factor, and the number of possible things you can do is very large essentially. we have not used any axioms here. So, by and large we try to build systems where axioms are not needed essentially, we just try to put in enough rules of inference which will work. But as a motivator for this method, here is another example. You are given a simple formula S and you are asked to derive P or not P. You are asked to derive. So, you must distinguish between this syntactic process of deriving formulas as opposed to the semantic process of looking at their truth values and saying this formula is true. So, if you look at P and not P, you can obviously say it is true, and it is quite trivial essentially, but the question is can you derive it in a system essentially. So, just as we said that it is not so straightforward to derive P implies P in Frege's system, it is not so, in fact you cannot derive if you are given only S and you are given all kinds of rules of inference, simplification, modus ponens, disjunctive syllogism, hypothetical syllogism, there are so many of them, it is not going to help you, you can never derive this from this essentially. But it turns out that Robinson's method, resolution method, is a complete method, it uses only one rule of inference and it does not need any extra axioms essentially. So, that is why it is so very attractive. It makes the task of programming it simpler, you simply have to take that rule, all you need to do is to decide on which data to apply it to essentially, because that is of course still not a straightforward problem. So, what is a resolution rule as it is called? So, we will look at a simple form, there is a more general form which we will may or may not look at it later. If you are given P or Q and if you are given not P or S, then you can derive Q over S. This is a resolution rule. In the simplest form, it could be P and Q or R also, it does not matter, it does not have to be just two things, but in the simplest form it has just two propositions here, two propositions here. And so, in the language of resolution method, we call each of these elements a literal, and resolution method works with formulas in what is known as clause form. And as far as we are concerned, in propositional logic, clause form is the same as conjunctive normal form. So, you have to first construct your formulas in clause form or conjunctive normal form. So, which means you cannot use things like P imply Q and so on. You have to, if you have a statement like P implies Q, you should convert it into not P or Q essentially. So, I will take it for granted that you can convert any given formula into clause form. Clause form or CNF is basically a formula of the kind C1 and C2 and Ck, where each Ci is of the form of D1 or D2 or Dr, let us say, and each Di is either a proposition or negation of a proposition. So, it has a very simple structured form. At the outermost level, it is a conjunction of clauses. So, C1 and C2 and Ck. Each clause is a disjunction of literals D1 or D2 or Dr. Each literal is either a proposition or its negation. So, the negation sign in some sense occurs in the innermost brackets, if you imagine brackets all over the place essentially. So, for example, you could start off by converting this problem into clause form by saying P is a clause, Q is a R is a clause, then not R or Q is a clause, then not P or not S or T is a clause, this corresponds to that, this is not R or S. So, I have converted these 4 sentences into clause form here. So, each one of them is a clause and I can think of it as P and R and this thing and this thing and this thing. I have a larger formula. Okay. Now, first of all we must ask ourselves, is this rule a sound rule or a valid rule of inference, and its validity is based on the validity of this equivalence P or Q or okay. So, I keep writing this, I just should be consistent. Actually, we need this larger equivalence to argue about what we are doing, but in practice the only thing you need is this and this implies this, which means P or Q and not P or S implies Q or S. So, for the rule to be sound, you must show that this implication is a tautology. It is a rule of inference that we have. If you see this and if you see this, then you can produce this. And remember that unlike the modus ponens rule that we talked about earlier, these are not patterns, in the sense that you can't plug in any arbitrary formula here. This is a clause, this is a clause and this is a clause, which means the constituents are all propositions or negations of propositions. It is not arbitrary formulas essentially. But you take any such 2 clauses. So, if you want to describe this rule, if you get one clause C1 and you get another clause C2 and one of them has a literal and one of them has a negation of that literal, then you can produce a clause in which you add up all the literals here and remove the what is cancelling each other in some sense. So, when you talk about clause forms, we also, instead of writing it as C1 and C2, we often write it as C1 comma C2 comma Ck. So, we think of it as a set. Likewise, this one D1 comma D2 comma Dr, where the comma is interpreted appropriately and in this outer level and or in the inner level. Sorry?
The equivalence that you have written, the clauses should be joined by and.
Yeah. So, the rule of inference requires this implication to be true, but we are going to be interested in this, as we will see in a moment why that is the case. So, this is called the resolvent. Is this called a resolvent? I always keep getting confused. Okay, let us call this a resolvent. Whenever you add the resolvent to the set of clauses, then the 2 sets of clauses are equivalent essentially. So, in other words, what we are saying is that we can keep adding clauses to this set. Okay. So, the resolution method works as follows, that you start with a set of initial clauses, let us call them C1, C2, C3, Ck, and then you replace or you add one more clause to this, which is the first resolvent, which means you are saying that this set of clauses. So, I am using a comma here and you should not get confused, this comma is equivalent to an and here, or you can write and just to be safe. So, I have added one more clause here, then I can add one more So, what I am saying is that I keep adding these resolvents to my set of clauses, and what I get is an equivalent set of clauses essentially. Okay. This set is equivalent, logically equivalent to this set is logically equivalent to this. So, you must prove that this is indeed the case essentially. So, once you prove this, it is easy to prove this, because from the right hand side to the left hand side it is trivial, from the left hand side to the right hand side it is based on this, that you are adding this extra clause q or s, and then you can basically show that this is a tautology. And I keep doing this till I get a clause which looks like, till I get a formula which looks like this. This is called the empty clause. Till I generate an empty clause. So, what am I doing? I am starting with a set of clauses C1, C2 up to Ck, and I added the first resolvent R1, then to this set I added R2, then R3, then R4 and so on till RL, and then at some point I was able to generate the empty clause, and I added the empty clause to this set, and that is when actually the algorithm terminates. So, what is the algorithm? Algorithm says take any two clauses which can be resolved, which means one of them has a literal and the other one has a negation of that literal, resolve them, produce a new clause and add it to the set. Then pick any two clauses, apply the resolution rule, and keep applying the resolution rule, keep adding clauses till at some point you generate the empty clause. How do you generate the empty clause? If you see a clause like this P, and if you see a clause like not P, so you can see P or nothing, not P or also nothing. So, when you apply this same rule here, there is no Q, there is no S. So, all you are left with is an empty clause, which sometimes we write with a box, sometimes we write with this, but basically it is an empty clause, and an empty clause stands for false, or it is always false essentially. So, I have jumped a little bit ahead from the natural deduction style of proof. In natural deduction style of proof, we said that we keep adding new formulas and we terminate when we find the formula that we are interested in. Here I have already jumped ahead and said that the resolution method keeps adding new formulas and it terminates when you generate the empty clause. When you find two clauses like this, and so this box is also used to denote an empty clause, this bottom also can be used to denote an empty clause, but basically an empty clause stands for something which is false, and the resolution method terminates with an empty clause, and we will see in a moment why, or I will tell you in a moment why. But what is the implication of this? What is the implication of the fact that you have added the empty clause to your set of clauses? You have to go back and see what are we saying here. We are saying that this set of clauses is logically equivalent to this set of clauses, which is logically equivalent to this set of clauses, and so on, which is logically equivalent to this clause. Now, what is the truth value of this clause? It is false, because it is something and something and something and something and something and false. So, this whole formula evaluates to false, which means this is false, which means this is false, which means this is false. I could have used the resolution method to say terminate, for example, in that example that we are doing, terminate when you generate T essentially, but we are not doing that. We are saying terminate when you generate an empty clause, which means we are trying to show that these formulas are all unsatisfiable. That is why this method is called the refutation method. it is used to show that a formula is unsatisfiable. A formula, when I say this is one large formula, right, it has got many clauses inside it, and it is used to show that a formula is unsatisfiable. And the reason why the resolution method is implemented in this manner is because it has been shown that the method is complete if you want to derive the null clause. It is not necessarily complete if you want to derive any arbitrary clause, which may be entailed by the system. So, remember, completeness means whatever is entailed can be derived essentially. The resolution method is complete for showing that a formula is unsatisfiable. If you give it an unsatisfiable formula, there will be a derivation which will derive the null clause from the set of unsatisfiable formula. Is that going to help us? We are not interested in unsatisfiable formulas, or are we? Could we be interested in unsatisfiable formulas? So, that is a question I asked you earlier in the last class. We have three kinds of formulas. One is valid formulas, which are always true under all valuations. There are satisfiable formulae which are true under some valuations. So, for example, P implies Q is true in under certain valuations. Then there are unsatisfiable formulas which are not true for any valuation, which are false for all valuations. And essentially what we are saying is that if you have an unsatisfiable formula, then you can test it using the syntactic procedure of this resolution method, which means keep applying the resolution method, and you will be able to derive the null clause. And so, first of all, you have to convince yourself that deriving the null clause is indeed showing that it is unsatisfiable, because of this equivalence. This whole formula is equivalent to the one before that, which is equivalent to one this, which is equivalent to this, which is equivalent to this, which means the original set that I started with is shown to be unsatisfiable. And remember that everything is to be expressed in clause form eventually. So, if I could, so I have that problem to solve. Okay. If you look at the top 5 lines there, I have 4 premises given and 1 conclusion to be drawn. Can I sort of produce an unsatisfiable formula from there? So, the process is straightforward. So, let us look at the clause form here. Okay. So, I have C1, C2, C3, C4, C5. What am I trying to do? If I look at it my logical notation, I am trying to do this C1, C2, C3. So, I am saying that given this 5 clauses or those 4 statements which are equivalent to 5 clauses, because this is a AND statement, it has broken down into 2 clauses, because the clause form says that a clause has only the disjunction side inside. So, P becomes a separate clause, R becomes a separate clause, this becomes R or Q, this becomes not P or S or T, and this is anyway not R or S. So, what I am really trying to do is this, that can I derive T from these clauses. Now, if you go to the back to the deduction theorem, it said that if you can do that, then you should be able to derive C1 and C2 sorry. So, remember that is what the reduction theorem said, that you could take, actually you could do it one by one, but eventually you will come to this formula, and I will leave that as a small exercise, because we are also shown somewhere in between that if you have P and Q and the whole thing implies R, then it is equivalent to saying P implies Q implies R. So, the 2 formulas are simpler. So, eventually you can, all the ANDs can come together here. So, this is a set of premises implies the conclusion is what you are trying to show to be true. So, what are you trying to show? You are trying to show that this formula, this larger formula is a tautology. What I have with me is a method which can show that a given formula is unsatisfiable. So, can I bridge this gap essentially? So, that is why I asked you this question. There are these three kinds of statements: valid statements, satisfiable statements, and unsatisfiable statements. If I take a negation of a formula, where does this, how do they get related to each other? So, if I take a negation of a satisfiable formula, for example, or if I take the negation of a valid formula, or I take a negation of an unsatisfiable formula. So, there is a clear relation, and you need to think a little bit about this, between the valid formulas and the unsatisfiable formulas. A valid formula is true under all valuations, which means every row in the truth table it will end up with true. If you take the negation of that formula, then every row will end up become false essentially. So, I have this, I am trying to show that this is true, which means you show that this negation of this C1 and C2 and C3 and C4 and C5 implies T is unsatisfiable. So, instead of trying to show that this is a tautology, which means it can be derived, I am assuming a sound and complete system. Instead of trying to show that it is a tautology, I can say that take its negation and show that it is an unsatisfiable formula. So, you must convince yourself that this is a sound step, that if I take a tautology and convert it, take its negation, it becomes unsatisfiable. Okay. So, I have produced now what I think is an unsatisfiable formula, and of course, to check whether it is unsatisfiable, instead of constructing a truth table, I will use the resolution method to check whether that is the case. Now, just a series of steps. If I were to take this not inside, so I have to convert this into clause form. Remember that the resolution method applies only to clause form. So, if I take this not inside, I will get not of C1 C5 or T. So, remember this equivalence which said that alpha implies beta is equivalent to not alpha or beta. So, this whole thing I am taking as alpha. So, I am taking not of this alpha and or this T, and then when I push this not finally inside, what I will get is C1 and C2 and C3 . So, that is the logically equivalent formula essentially. So, now I have the formula that I am interested in clause form essentially. Okay. So, each of these is a clause, we have already said that, see, each of them is a clause. So, we and this is just a literal. So, not T is also a clause essentially. So, now we have a approach to using the resolution method, which is that you take the set of clauses that are given to you, which is the premises, you take the conclusion and take its negation not of T and add it as a clause, and the claim is that this set is unsatisfiable. Is it unsatisfiable? We can try and show that using the resolution method essentially. So, resolution proofs are usually shown as directed graphs or directed acyclic graphs. So, resolution DAGs they are called. So, let us try and do the resolution method here. So, I will just write the clauses again now. This is P, this is one clause, this is R, this is not R or Q, not P not S or T, not or S. So, these are the 5 given clauses, and the negation of this is T. I have the 6 clauses. So, C1 to C5 and negation of the goal or negation of the conclusion, which is a 6th clause. So, before we proceed, you should be able to see that this is really proof by contradiction essentially. What you are saying is that given these clauses, assume that the conclusion is not true and then show that the whole set becomes unsatisfiable, which means of course, if this is unsatisfiable, the only reason why this could be unsatisfiable if this last clause was not correct, which means C1, C2, C3, C4, C5 are anyway given to us. You cannot assume them to be false. The only reason why this formula has become false is because not of T is there. So, not of T is making it false. So, therefore, not of T must be false itself, which means T must be true essentially. So, it's basically proof by contradiction. So, that leaves us with the small task of finding a proof, and what is a proof? A proof is a derivation which ends in a empty clause or a null clause. So, let us see, we can take any 2 clauses and resolve them. So, for example, well, in this there are not too many choices, but in general a larger problem will offer you many choices, but in this case you do not have too many. So, let us say you take this and you get negation of Q. So, you must see that what I am doing is applying the resolution step. From this clause I am removing R, from this clause I am removing not of R. So, from this clause I am removing R, from this clause I am removing not of R. So, what I am left with is Q. Then is that correct? Okay. So, this Q is not very useful for me. I can take this and I can get S. So, remember this is a directed graph. I can take any 2 clauses. So, this is just a set. So, I can take now this and this, I get not P or T. See, I can resolve this with this or I can resolve this with this, but just for the sake of argument, let us say we resolve this with this. So, you can see that actually we have derived T. We have actually derived T, which of course, as we know from the natural deduction method, it is quite possible to do that essentially. But our method does not stop here. Our method says now you must derive the null clause. So, you can see from this and this, you can derive the null clause. So, this graph represents the proof that the given set of clauses is unsatisfiable, and the proof holds because of this equivalences that we have seen, that we are keep adding these new things, and in the end we added an empty clause, and an empty clause basically stands for false. You can see that an empty clause is saying T is true, and at the same time you are saying not T is true. So, obviously, that stands for false or contradiction. So, if you can derive an empty clause, then we have shown that this set of clauses is unsatisfiable, which means this large formula is unsatisfiable, and it can only be unsatisfiable if not T were false. Nothing else can be false here, because those are premises given to us. So, if not T is false, then T must be true. Okay. So, let us quickly just look at this modus ponens rules. What does modus ponens says? It says P, or it says in terms of literals at least, P and P implies Q, and you can do Q. Now, you can see that if I were to convert it into clause form, I have P and not P or Q, and I am deriving Q, because we know that these two are equivalent essentially. So, you can see that modus ponens is just one example of the resolution rule being applied. Or if you look at modus tollens says P implies Q and not Q implies not P. Then you can see that this is again not P or Q and not Q and not P. So, again in this form when you replace P implies Q with not P or Q, you can see it is the same resolution rule being applied. Take a literal from here Q, take the negation from the other one and cancel that, and whatever remains is what you have. So, all these rules as you can see are special cases of the resolution rule that we have stated here. In fact, the resolution rule is more general than this. As we saw in this example, it does not have to be only 2 literals, it can be more than 2 literals. So, we used not P or not S or T and cancelled it with not with S. So, we removed S from here and what was left was not P or T. So, that is the resolution method is a sound and complete proof procedure for the case of propositional logic essentially. It was introduced in 1965 and since then a lot of theorem proving work is based essentially on the resolution method essentially. So, it is the most popular way of proving theorems, but so far we have seen only propositional logic. So, what is the language of propositional logic? We have a set of propositions and they could stand for anything and we do not know. The only thing that is sort of this system is solving out for us is the meaning of the connectives, that when you have these connectives, what do the sentences mean, what do compound sentences mean, when are they true, and then we can sort of extend that to truth value of entailment essentially. If you go back to the example we started with, this the Socratic argument, all men are mortal, Socrates is a man, Socrates is mortal. This is beyond our reach. To talk about this argument is beyond the reach of propositional logic, because you cannot really do anything with these sentences essentially, because what you need here is to somehow understand what do you mean by all, and then the relation between being man and being mortal, and then to say that the same relation between being man and being mortal will apply to Socrates, because Socrates happens to be a man. Now, this is not possible in propositional logic, because if you say this is P, this is Q, then there is nothing you can really do. There is no logical connectives implied here. You could say, for example, M stands for man and something else, R stands for mortal, and you could say M implies R is, but you can see that this notion of all is missing here essentially. To handle this, we need to go to first order logic. Which is a more expressive language, which allows us to look inside sentences. Remember, in propositional logic, a sentence is atomic, and the only thing you can say about a sentence is that in our mind it stands for something and whether it is true or false. But in first order logic, a sentence can be broken down into its constituents, and it can look at the relation between the different constituents. So, what is the relation between being a man and being mortal, and then saying that this relation carries forward to Socrates, because Socrates is a man, therefore, the same relation must apply to him, that he is also mortal. That is possible in first order logic. First order logic will introduce the notion of individuals, men, Socrates, and so on. In propositional logic, there are no individuals, there are only sentences, and sentences can only be true or false, whereas individuals are things which can participate in relations essentially. So, in the next class, when we meet on Wednesday, we will look at first order logic, and we will look at all these proof methods in the context of first order logic, plus some extra rules that we may need essentially. Okay, so we will stop here.